Okay, in chapter 6, which is our next chapter to cover, we're going to study numbers, okay? And we already talked about them a little bit in chapter 2. Let's do it again by way of a review, and then we're going to dig into them deep. So recall that the natural numbers are just the easiest numbers, 1, 2, 3, 4, and so on. The mathematician Kronecker once said that God gave us the natural numbers and all the rest is the work of men. In other words, those are the most basic things and everything else is kind of people just kind of playing with them. So anyway, it's easy to see where the natural numbers come from if you're trying to count sheep or count the number of stones in your pocket or something. Before you even had language very well developed, you were probably people kept track of them on their fingers and had to count. So those are the natural numbers. Then, as soon as you start getting involved in social societies and so on, you start getting into negative numbers. Why would you have negative numbers? Suppose maybe a cow is worth four goats, and so you give your neighbor a cow, but he only has 3 goats to give you in return. Then you might kind of keep mental track, or he would keep mental track, that he owes you 1 goat. In other words, he has 1 cow, but he has a negative goat. So as soon as you get into a little more complicated situations than just counting, you end up with negative numbers. So those are the integers, okay? And so -3, -2, -1, 0, 1, 2, 3, and so on. So those are the integers. Then, as soon as you start measuring things, you get into the rational numbers. Because, for example, if this is 1 foot right here, you might measure something which is this big. And so it's 1 foot, but it's some part of a foot as well, maybe 1 1/3 or something like that. If you do any baking, you work with fractions. If you're a carpenter or builder, you need to work with fractions. And so those are the rational numbers. Stands for ratios, and so the way you write them is anything of the form P over Q, where P and Q are integers, and recall that Q can't be equal to 0. Doesn't make any sense to divide by 0. We'll talk about that a little bit later. And so then finally you have the real numbers, and the real numbers are the ones that correspond to the number lines. So you have 0 here and 1 there and 2 there and 3 there and -1 there and -2 and so on. So you have all those. And so the first question that comes to mind then is there any difference between this set and this set? Perhaps all the points along the number line are themselves rational numbers. If you just pick a point on the number line and designate it, perhaps that's 3/2, or if not 3/2, maybe it's 1.50013654267113. Maybe that's what that point is. And so perhaps, and that's a rational number because you could write it as this whole thing over however many zeros, 1 with a whole bunch of zeros, just like 1.53 is equal to 153 over 100. So similarly, this is a rational number in the same way. So perhaps all of these things are rational numbers. Is there anything there which is not a rational number? The Pythagoreans, who were the original Greek society, Greek fraternity of about 2,500 years ago, they thought that there were. They thought that every number along here was a rational number. And then one of them had this discovery. He said, okay, remember the Pythagorean theorem. Pythagorean theorem says that if you have 3 sides of a triangle, let's just call this C for the last side here, that this thing squared plus this thing squared equals this thing squared, if it's a right triangle. So 1 squared plus 1 squared is equal to C squared for this particular triangle. And so 1 squared is 1, so it's going to be 1 plus 1 is C squared. 2 is equal to C squared. So C is by definition the square root of 2. That's what we mean by the square root of a number. It's the number such that when you square it, in this case, when you square it, you get 2. So here's the number line. here you can make the number line here. You can take a compass if you want to and draw a nice, whatever this distance is, draw that same distance right there. And then you can make yourself this square right there, and you can find that hypotenuse. And we see that that hypotenuse is the square root of 2. And now that you have the square root of 2, you can come down and it hits the number line right there. So right there is the square root of 2. So the square root of 2 is on the number line. Okay? The square root of 2 is on the number line. Everyone agreed? So that's not such a big deal. The Pythagoreans agreed, okay, the square root of 2 is on the number line. They just figured that the square root of 2 was some rational number. If you look at what number times itself gives you 2, it turns out that 1.41 times 1.41 gives you something pretty close to 2, maybe 1.98, I can't remember exactly, but it gives you something pretty close to 2. And so they figured, well, if you go out far enough, it'll stop at some point, and that number times itself will give you exactly 2. That's what they figured. And then someone came up with the following proof. Okay, here's a theorem. I'm going to write it THM for theorem. Square root of 2 is not a rational number. That means it cannot be written as the ratio of one integer over another. And there's various ways to prove it. The author in the book has one way to prove it, which is kind of a standard way. Here's another way I discovered a while ago in a journal, which I think is really clever. I'm going to prove it to you. Okay? So this is called a proof by contradiction. So here's a mathematical proof. We're going to suppose it is. Suppose it is a rational number. Okay? If it is, that means that there are numbers p and q such that p divided by q gives you the square root of 2. That's what it means to be rational. And we can assume that p and q are the smallest such numbers. Okay? Because, for example, if you had 14 over 21, that's equal to, you can reduce that to 2/3. That's exactly equal to 2/3, but those are the smallest numbers. You can't reduce this any further. So this has been reduced. These are the smallest possible numbers p and q, such that p over q gives you the square root of 2. Okay, you with me? So now watch what we can do. If we multiply the q on both sides, we're going to get p is equal to the square root of 2 times q. Okay, takes a little bit of algebra. And then if this is equal to this, we're now going to square both sides. If you square both sides, take this thing squared, you're going to get p squared. And if you square this side, if you square a times b, you have to square them both. Okay, so if I square the square root of 2, I just end up with 2. And if I square q, I'm going to get q squared. Okay, so you get that. So those numbers satisfy that. Let's draw ourselves a picture which can be represented by this. We're going to let that be a length of p. I'll write p here, it says square. And I'm going to let this be q. I'm going to make it just a little bit smaller. Like so. Okay, so this side has length p, And this side right here, these small ones, are length q. I'll put them like that. Okay, you with me? Let's figure out what these other sides are. This is p and this is q, so this right here is going to be p minus q. Agreed? All of these are p minus q, and so on. Okay? What about this length? This length right here is going to be q. Whoops. And then once you have q, you subtract this length, but that length is p minus q, so I'm going to subtract p minus q. And when I subtract that, I'm going to get q minus a negative q is 2q. Q minus a negative 2 is 2q. 2q minus p. Okay? 2q minus p. So this one right here is 2q minus p, as is this one. 2q minus p. Okay? Now, we're almost done. I like this proof because it's just drawing a bunch of pictures. First of all, remember what we're saying here. We're saying that this area right here, which is p squared, that area is equal to 2q squared. There's 1q squared right there. There's another q squared. In other words, we're saying the area of this floor, if we wanted to think of it as a floor covered by two carpets, by two rugs, here's the floor right here, and here are your two rugs. You have a rug right there, and you have a rug right there. The area of this rug is q squared. The area of this rug is q squared. So 2q squareds, the area of both of those rugs, is equal to the area of this whole floor. Okay, so notice, the area of these two rugs is equal to the area of the whole floor. You got some overlap here. See that? There's the overlap. And here is the area of the floor which is not covered by those two rugs. So since the area of these two rugs has to be equal exactly to the area of this floor, that means that the area of overlap has to be exactly equal to the area which is not covered. The area of overlap is 2q minus p quantity squared, and the area that's not covered is p minus q squared, and we have two of those. See that? So notice, what we claimed here was that this thing here was satisfied for the smallest values of p and q. We said p and q were the smallest values that made that true. Here's p, and here's q. But now we've got two other numbers. This is a natural number, and this is a natural number. And so here we have a natural number. Instead of p, this thing squared is equal to 2 times this thing squared, so it has the same relationship as this, but these two numbers are obviously smaller than these two. Look, p minus q, that's only that big, and 2q minus p is only that big. So there's a contradiction, okay? And this is a special kind of mathematical proof where to prove something is true, you assume it's not the case, and then you get a contradiction. So in other words here, we wanted to prove that this is not a rational number. The way we proved it is by assuming it was a rational number. And once we assumed it was a rational number, we got ourselves a contradiction, which means that this assumption must have been wrong. So therefore, the square root of 2 is not a rational number. And there's a whole legend that when the first Pythagorean showed all of his Greek fraternity buddies that square root of 2 is not rational, they were so upset because they were so sure that these were all rational numbers that they took the guy out into the Mediterranean and dumped him overboard and got rid of it, got rid of the evidence. Okay? So pretty cool. So anyway, so that shows that here's the real numbers right here. Here's the rational right there. I'll use the notation for rational right there. Here are the integers right there. And then here's the natural numbers right there. So natural numbers are again like 1 and 3. This would include 0 and -5. This would include all these, but would also include 3/5 and -14/3 and so on. And then what are the numbers which are real but are not rational? Well, the square root of 2 is 1. That's the one we just proved. It turns out that most all the square roots, most all the cube roots, all those things are these are called irrational numbers. Irrational meaning that they're not rational. Okay? Pi is a famous one. We'll talk about some of these later. Okay? So there you go. So that's all important stuff. Okay. Let's do a couple other things. This was all section 1. Oh no, one more thing let's do in section 1, and that is to talk about absolute value. Sometimes when you're talking about the number line, you want to know how far away one number is from another. So like if I ask, how far away are these two from each other? Well, you could either go 4 minus 1 to get 3, because that's the distance they are away. Or if you went in the other direction, 1 minus 4 is equal to -3. Now, of course, the distance from here to here is the same as the distance from here to here. So if you just want distance, you don't care whether you don't want it to be negative. Distance itself is a positive quantity, so it doesn't matter which one I subtract from the other. I want it always to be a positive number. So to always get a positive number, you put absolute values there, which means that if this thing is positive, you get the same thing as before. If this is negative, you take the opposite of it, and so you still get 3. So the absolute value of this is of a number is here's the definition of it. The absolute value of a number is just equal to that number if that number is positive, and it's the opposite of that number if the number is negative. So if the absolute value of 5, since 5 is positive, it's just equal to 5. The absolute value of -5, well, -5 is less than 0, so what do you do with that -5? You take the opposite of -5. What's the opposite of -5? That's back to 5 again, right? So it's equal to that. So that's what the absolute value is. And as I say, that deals with distance. Here's another way in which it's used. You might say, what are all the values of x which are less than 3 units in size? So all the values of x which are less than 3 units in size, or less than 3 units from the origin. There's the origin right there. You'd say, well, that's everything from -3 to 3. So this is the same as saying that x lies somewhere between -3 and 3, because the size of x is less than 3. So all these numbers in here, the size of all those numbers is less than 3. If you did something like this, x minus 5 is less than 3, then you do the same sort of thing. You take this thing right here, x minus 5, and you put that between 3 and -3. It means that the size of this thing is between -3 and 3. And then, if you add 5 all the way along, you're going to get 5 plus -3 is going to be 2, less than x. Add 5 to this, you're going to get 8. So 4, 5, 6, 7, 8. So if I want to know what are all the points that are within 3 units of 5, here's my 5 right there. Here's my 5. What are all the points that are within 3 units of 5? It'd be everything from where to where? From 2 to 8. Those are all the numbers between 3 and 5. Okay? Very good. So that covers 6.1, and we'll get started in 6.2 in the next section.